Everybody is ready? So my name is Chung-Kil. I'm going to prepare this second verification session. We have 3 papers. The first paper will be about the CompCertCast and the Archmage, and Yonghyun Kim will give the talk.
Today I will discuss end-to-end verification supporting integer pointer casting. This work addressed the challenge of verifying both program specification and compiler correctness for programs that use integer pointer casting. Let me start with the motivation. Integer pointer casting is a key feature in C programming, widely used in critical systems like Linux kernel. Our goal is to verify C programs that use integer pointer casting in end-to-end manner from specification all the way down to assembly code. What exactly do we mean by end-to-end verification? As shown in this diagram, we have 3 key components: specification, source code, and assembly code. End-to-end verification consists of 2 major parts. First, compiler verification, which ensures the compiler correctly translates the source code to assembly. Second, program verification, which proves that the source code satisfies its specification. By connecting these 2 verification steps, we can prove that our final assembly code correctly implemented the original specification. Let's explore the key challenge in memory model design, namely the tension between supporting integer pointer casting and enabling compiler optimization. To see this, consider 2 contrasting approaches: the concrete model and the logical model. In concrete model, every memory location has a specific integer addresses. As pros, this makes it highly intuitive for programmers and naturally support integer pointer casting, which is essential for many real-world C programs. However, as cons, the concrete model makes it very difficult to perform sound compiler optimizations. Before proceeding to the logical model, let me illustrate the pros and cons of the concrete model with a simple example. Here's a simple program where compiler performs constant propagation like this. Let me examine this code line by line. Line 1 and 2 declare 2 characters arrays initialized by 0. Line 4 contains the key operations, checking if array A and B are contiguous in memory by comparing address right after array A and the beginning of array B. If contiguous, line 5 writes 1 to A1, which is the same location as B0. Line 6 prints B0, which should be 1 after the previous update. Oh, sorry. However, this conflicts with constant propagation optimization. Most compiler would propagate B0's initial value 0 to the print statement, as they viewed line 5 as modifying array A, not B. Consequently, the compiled code prints 0 instead of 1. This optimization contradicts the concrete model's requirement to print 1. Moving to the other end of the spectrum, we encountered the logical model, where each memory location is assigned a logical address. This approach offers significant advantages for compiler optimization justification. However, its major drawback is that most integer pointer casting patterns become invalid under this model. Let me demonstrate both these benefits and limitations using our previous example. In logical model, A and B are located in separate logical blocks, L1 and L2 at offset 0. When we reach line 4, comparison, we compare pointers from different memory objects, where the pointer L1, 1 is out of bounds. This triggers undefined behavior in the logical model because we branches on comparison between an out-of-bound pointer and a pointer from a different logical block. When the source has undefined behavior, any optimization is valid since undefined behavior means all possible behavior. This enables important optimizations like constant propagation. However, logical model has a crucial limitation. It struggles with integer pointer casting. Consider adding line number 11, where we perform an integer to pointer casting followed by multiplication. The logical model produces an undefined value because logical pointer do not have underlying integer address. This shows why the logical model can't properly handle integer pointer casting patterns. This leads us to our central challenge. Can we create a model that supports both integer pointer casting and compile optimizations? Here's our key contributions. First, we developed the Archmage memory model that balances concrete and logical models, supporting both integer pointer casting and compile optimization soundly. Second, we built CompCertCast, extending CompCert with Archmage to verify compilation from source to assembly. Third, we create Archmage logic for verifying high-level specification of program using integer pointer casting. Together, these forms an end-to-end verification framework for C program with integer pointer casting. Now, let's move to the memory model part first. Before presenting our Archmage model, let's examine its predecessor, the quasi-concrete model from PLDI-15. As shown here, quasi-concrete model found a middle ground between concrete and logical models, handling most integer pointer casting patterns while justifying optimizations. However, it could not handle one-pasty and pointer patterns. This limitation motivated our development of the Archmage model. Let's examine how the quasi-concrete model works and where it fell short using this example. This code is similar to our previous example, with changes highlighted in red, where we convert the pointers A and B into integers IA and IB at line number 4 and 5, and then compare two underlying integer addresses instead of their logical representation at line number 7. Then we convert IA plus 1 back to pointer and compare it with the original pointer A. In quasi-concrete model, we allocate to two logical blocks at line number 1 and 2 like logical model. Line number 4 and 5 cast pointer A and B into integers. Remember, where the model non-deterministically assigned them physical addresses. Let's say OX100 and OX101 in this particular execution. At line 8, here's a key issue. Address OX101 is special. It could be either L1.1 for one past the end pointer of the array A, or L2, 0 for the start of array B. The quasi-concrete model requires that integer cast to pointer must be in bounds, so forcing OX101 to resolve to L2, 0. This creates problem. According to C standard, this comparison between A and A1 should be well defined because they are derived from same block, L1. And they are offsets within one past the end of the block. However, the model sees them as pointers to different blocks, L1 and L2, thereby giving an undefined value. This shows why quasi-concrete model cannot handle one past the end pointer patterns. Let me introduce our Archmage memory model. Let's see how Archmage supports the one past the end pointer pattern in this example. First, Archmage handled memory allocation and pointer to integer casting in the same way as the quasi-concrete model. However, at line number 8, Archmage takes different approach. When converting an integers to a pointer, it uses lazy valuation, keeping the integer value OX101 until the pointer representation is needed. Now, see how this approach solves the problem. At line number 9, Archmage compares L1, 0 with OX101 as follows. First, it converts both to pointers via to pointer, and also convert both to integers via to int, and then evaluate both comparisons according to the logical memory model semantics. While 2PTR yields undefined value, 2int succeed with true, then Archmage selects this defined value true as a final result. Why this is good? At the casting time in line number 8, we cannot know if the programmer means a one past the end pointer or the start of the next object. The intention becomes clear only when the pointer is used, like line number 8. Archmage's strategies of trying both interpretation captures this reality. Also, this design is sound because we proved that when both strategies given different defined value, they always agree. Additionally, we proved that integer refines pointers in Archmage. That is, integer representation have more defined value than their pointer representation. This allows safe replacement of pointer representation into integer representation during compilation. Please remember this. Let's move to compiler verification part of our work. We extended CompCert, which uses logical model to support integer pointer casting by applying Archmage. And let me introduce 3 key challenges in developing CompCertCast. First, we needed to update the compiler while keeping performance overhead minimal. Second, we had to modify CompCert's proof technique, maximizing reuses of its original proof. Third, we added a new layer for assembly without logical pointers, since real hardware's only understanding physical addresses. Now, I will show you how we tackled each challenges. For compiler performance, we developed cast propagation. It's a new optimization to reduce register pressure in register allocation. And we extended value analyzer of original CompCert to track stack pointer casting. For CompCert's proof structure, we extended memory relation to handle integer addresses. And we extended simulation relations to handle non-determinism and out-of-memory behaviors. For assembly level, we added a layer proving assembly without logical pointers refines assembly with logical pointers. Among the 3 challenges, I will present the first is in more detail. If you can find the details of the others in the paper. In the original CompCert, pointer to integer casting is treated as equality. This allows efficient register allocation. A single register, in here EBX, handles both variables P and I. However, Archmage handles pointer to integer casting differently. It's not equality. So, register allocation must treat P and I as a different variables and with overlapping lifetimes. So, we need two registers in this case. This reduces efficiency of register allocation. This is the problem. This is where cast propagation helps. Archmage guarantees that integer refines pointers, letting us safely replace pointers with their underlying addresses. Using this property, cast propagation replaces P with I. It separates their lifetimes. With separated lifetimes, register allocation can return to using just one register. In here, EBX. Now, let me share our implementation result and performance achievements. On the implementation side, our extension to CompCert added about 24 to original code base to support integer pointer casting. And cast propagation optimization requires approximately 6,600 lines of code. New physical assembly layer needed around 3,000 lines of code. In terms of performance, we achieved three key results. First, we maintained full support for all CompCert optimization passes from C-Lite to assembly. CompCertCast source level language is C-Lite, not CompCert-C. Second, when compiling CompCert's own benchmark that do not use integer pointer casting, our compiler produced identical assembly code to the original CompCert. Finally, through cast propagation, we achieved reduced register pressure, which we checked with our custom test program. Let's move to last part. We developed Archmage logic, extending separation logic to handle integer pointer casting. Most of our operations follow standard separation logic principles. Nothing new here. The key changes is our pointer to integer casting rule. When casting a pointer to an integer, we create this predicate that links the logical and physical addresses under one block identifier. This casting relation can freely relate integers and pointers, allowing either type on both sides. This relation provides two important properties. First, this relation forms equivalence classes under each block identifier. Second, pointers within these casting relations are freely substitutable. These rules enable sound reasoning about programs using integer pointer casting. Also, we built Archmage logic on the CCR framework and verified complex structures like XOR list, and now ported both the logic systems and proved to the CRIS framework. In summary, we developed an end-to-end verification framework for C program with integer pointer casting through these contributions. Thank you for listening.
All right, thank you. We really only have time for one question. The next speaker, please go to set up. Yeah.
Thanks. That's an impressive amount of work. I was wondering, with these rules that you have for like lazy integer pointer conversion, it sounds like I could use the same, like I cast an integer to a pointer and I use the pointer multiple times to actually access different allocations, and it would lazily kind of snap to whatever allocation it happens to be at that moment. Is that correct? And if yes, why is that not a problem?
You mean each time I use that integer representation pointer, then
Each time you said you determine the logical allocation again, but like I use it once, then I subtract one, I use it again. Now I might use different allocations, which wouldn't be possible under like a PNVIA UDI model.
Maybe we can move this offline.